In Part 1 of Lecture 7, we will discuss memory fundamentals. In a uniprogramming system, main memory is divided into two parts. One part for the operating system, the resident monitor or kernel, and other part for the program currently being executed. In a multiprogramming system, the user part of memory must be further subdivided to accommodate multiple processes. The task of subdivision is carried out dynamically by the operating system and is known as memory management. While surveying the various mechanisms and policies associated with memory management, it is helpful to keep in mind the requirements that memory management is intended to satisfy. These requirements include relocation, protection, sharing, logical organization, and physical organization. We will be talking about these one at a time. In a multiprogramming system, the available main memory is generally shared among a number of processes. Typically, it is not possible for the programmer to know in advance which other programs will be resident in main memory at the time of execution of his or her program. In addition, we would like to be able to swap active processes in and out of main memory to maximize processor utilization by providing a large pool of ready processes to execute. Once a program is swapped out to disk, it would be quite limiting to specify that when it is next swapped back in, it must be placed in the same main memory region as before. Instead, we may need to relocate the process to a different area of memory. Thus, we cannot know ahead of time where a program will be placed, and we must allow for the possibility that the program may be moved about in main memory due to swapping. These facts raise some technical concerns related to addressing, as illustrated in the slide. The figure depicts a process image. For simplicity, let us assume that the process image occupies a contiguous region of main memory. Clearly, the operating system will need to know the location of process control information and of the execution stack, as well as the entry point to begin execution of the program for this process. Because the operating system is managing memory and is responsible for bringing this process into main memory, these addresses are easy to come by. In addition, however, the processor must deal with memory references within the program. Branch instructions contain an address to reference the instruction to be executed next. Data reference instructions contain the address of the byte or word of data referenced. Somehow, the processor hardware and operating system software must be able to translate the memory references found in the code of the program into actual physical memory addresses, reflecting the current location of the program in main memory. Each process should be protected against unwanted interference by other processes, whether accidental or intentional. Thus, programs in other processes should not be able to reference memory locations in a process for reading or writing purposes without permission. In one sense, satisfaction of the relocation requirement increases the difficulty of satisfying the protection requirement. Because the location of a program in main memory is unpredictable, it is impossible to check absolute addresses at compile time to assure protection. Furthermore, Most programming languages allow the dynamic calculation of addresses at runtime, for example, by computing an array subscript or a pointer into a data structure. Hence, all memory references generated by a process must be checked at runtime to ensure that they refer only to the memory space allocated to that process. Fortunately, we shall see that mechanisms that support relocation also support the protection requirement. Normally, a user process cannot access any portion of the operating system, neither program nor data. Again, usually a program in one process cannot branch to an instruction in another process. Without special arrangement, a program in one process cannot access the data area of another process. The processor must be able to abort such instructions at the point of execution. Note that the memory protection requirement must be satisfied by the processor, which is hardware, rather than the operating system, which is software. This is because the operating system cannot anticipate all of the memory references that a program will make. Even if such anticipation were possible, it would be prohibitively time-consuming to screen each program in advance for possible memory reference violations. Thus, it is only possible to assess the permissibility of a memory reference, whether it is a data access or branch, at the time of execution of the instruction making the reference. To accomplish this, the processor hardware must have that capability. Any protection mechanism must have the flexibility to allow several processes to access the same portion of main memory. For example, if a number of processes are executing the same program, it is advantageous to allow each process to access the same copy of the program rather than have its own separate copy. Processes that are cooperating on some task may need to share access to the same data structure. The memory management system must therefore allow controlled access to shared areas of memory without compromising essential protection. Again, we will see that the mechanisms used to support relocation support sharing capabilities. Almost invariably, main memory in a computer system is organized as a linear or one-dimensional address space consisting of a sequence of bytes or words. Secondary memory at its physical level is similarly organized. While this organization closely mirrors the actual machine hardware, it does not correspond to the way in which programs are typically constructed. Most programs are organized into modules, some of which are unmodifiable or read-only, execute-only, and some of which contain data that may be modified. If the operating system and computer hardware can effectively deal with user programs and data in the form of modules of some sort, then a number of advantages can be realized. 1. Modules can be written and compiled independently, with all references from one module to another resolved by the system at runtime. With modest additional overhead, different degrees of protection, read-only, execute-only, can be given to different modules. It is possible to introduce mechanisms by which modules can be shared among processes. The advantage of providing sharing on a module level is that this corresponds to the user's way of viewing the problem, and hence it is easy for the user to specify the sharing that is desired. The tool that most readily satisfies these requirements is segmentation, which is one of the memory management techniques that we will explore in this lecture. As we discussed in Lecture 1, computer memory is organized into at least two levels, referred to as main memory and secondary memory. Main memory provides fast access at relatively high cost. In addition, main memory is volatile. That is, it does not provide permanent storage. Secondary memory is slower and cheaper than main memory, and is usually not volatile. Thus, secondary memory of high capacity can be provided for long-term storage of programs and data, while a smaller main memory holds programs and data currently in use. In this two-level scheme, the organization of the flow of information between main and secondary memory is a major system concern. The responsibility for this flow can be assigned to the individual programmer, but this is impractical and undesirable for two reasons. One, the main memory available for a program plus its data may be insufficient. In that case, the programmer must engage in a practice known as overlaying, in which the program and data are organized in such a way that various modules can be assigned the same region of memory, with a main program responsible for switching the modules in and out as needed. Even with the aid of compiler tools, overlay programming wastes programmer time. Second reason, in a multi-programming environment, the programmer does not know at the time of coding how much space will be available or where that space will be. It is clear then that the task of moving information between the two levels of memory should be a system responsibility. This task is the essence of memory management.